All right, welcome to The Explainer. Today we're going to pull back the curtain on some of the invisible forces that shape, well, pretty much everything around us.
So let's kick things off with a little riddle. What do honey, the air you're breathing right now, and the blood flowing through your veins all have in common? On the surface, they couldn't be more different, but it turns out they all play by the exact same set of universal rules.
That's it. They're all fluids. And the science that unpacks how they all behave, that's called fluid mechanics. So let's dive right in and get a feel for the key principles.
Okay, so here's the game plan for today. We're going to start with the absolute basics and then build on that, piece by piece. By the end of this, I promise, you'll see the world around you in a whole new way.
So first things first, what are we even talking about here? Well, fluid mechanics is just the science that looks at how fluids behave. And remember, that's not just liquids, it's gases too, whether they're just sitting there or zipping around. For this explainer, we're going to stick mostly to fluid statics, and that's just the fancy term for fluids that aren't moving. It might sound kind of boring, fluids at rest, but trust me, this is where you can really see the fundamental rules of pressure in action.
Okay, so to really get a handle on any fluid, we kind of need a language to describe it, right? Think of these next two ideas as, I don't know, a fluid's core personality traits. They tell us pretty much everything we need to know about how it's going to act.
First up, we've got density. You'll see it written as the Greek letter rho. It's really simple. It's just the mass of a fluid crammed into a certain amount of space. You know, how much stuff is packed in there. Like water has a density of 1,000 kilograms for every cubic meter. It's all about how hefty it is.
And the second key trait is viscosity. Oh, I love this one. It's basically how much a fluid resists flowing. You can think of it as its internal friction. You know, what makes some fluids feel thick and gloopy and others feel super thin and runny.
And this slide just makes it so clear, doesn't it? Take water. It's got super low viscosity. Its internal resistance is tiny, so its layers just glide past each other, no problem. It flows freely. But honey? Totally different story. It has super high viscosity, a ton of internal resistance, and that's exactly why it pours so slowly and deliberately.
All right, so now we have a way to describe a fluid. We know its density and its viscosity. Let's move on to the main event, the biggest force at play when that fluid is just sitting still: pressure. Now, we use that word all the time, but in fluid mechanics, it means something really specific.
So pressure is defined as a force spread out over an area. Simple as that. When a fluid is just chilling, it's pushing on any surface it touches, the bottom of your cup, the walls of a pipeline. That force spread out, that's what we call pressure.
Okay, but how does that pressure actually act inside the fluid? Let's do a little thought experiment. Picture a sealed plastic water bottle. Now, in your mind, squeeze it right in the middle. Does the pressure only go up right where your fingers are? Or does something else happen?
Well, a genius from the 17th century, a physicist and mathematician named Blaise Pascal, he figured this out. And what he discovered is one of the most important rules for understanding fluid pressure. The key takeaway is
That the pressure doesn't just hang out where you squeezed. Nope, it gets transmitted equally to every single part of the fluid in all directions at the same time. You squeeze that water bottle, and the pressure instantly spikes everywhere inside, pushing out on every single square inch of the plastic. And this little idea is what makes huge things, like hydraulic lifts, even possible.
Okay, so Pascal's law is huge. It tells us that at any single point in a fluid, the pressure is the same in all directions. But, and this is a big but, that doesn't mean the pressure is the same everywhere throughout, say, a giant swimming pool. There's another piece to this puzzle we need.
And you've definitely felt this. If you've ever dived down to the bottom of a pool, you feel that pressure building in your ears, right? That's the weight of all the water above you pressing down. The deeper you go, the more water is on top of you, and the greater the pressure gets. So this relationship has a name. It's called the hydrostatic law, and the formula looks like this: P equals rho gz. That just means the pressure P at any depth is the fluid's density, rho, times gravity, g, times how deep you are, z. This is exactly why dams have to be built way thicker at the bottom than they are at the top. They have to fight against that immense pressure from the deep water. Okay, so we've got these really powerful laws that describe how pressure works. But, you know, that's all on paper. How do we actually go out and measure this invisible force in the real world? Well, let's take a look at one of the classic and honestly most beautiful tools for doing just that. They're called manometers, and they are just these wonderfully simple devices that make an invisible force like pressure
totally visible. How? By using the weight of another liquid to balance it out. We're going to look at one of the most common kinds, the U-tube manometer. So here's how it works, step by step. The pressure from the fluid in the pipe, it pushes down on the liquid in the U-tube on one side. That, of course, makes the liquid rise up on the other side. All you have to do is measure that difference in height between the two columns. And if you know the density of the liquid in that U-tube, you can calculate the exact pressure in the pipe. It's like a physical equation balancing itself right there in front of you. Super clever. So let's do a quick wrap-up of what we've covered. We started with the personality of fluids, their density and viscosity. Then we hit the two big laws of fluid pressure, Pascal's law, saying pressure is transmitted everywhere, and the hydrostatic law, saying pressure increases with depth. And finally, we saw how a simple U-tube manometer lets us actually see and measure that pressure. The big takeaway here is just how these few simple rules govern so much of the world that we live in.
And I'll leave you with one final thought to chew on. We know pressure is force over area, and we know from Pascal's law that pressure is transmitted equally. So, how can a small push on a tiny piston in a hydraulic lift create enough force to lift a car that weighs tons? The answer is right there in Pascal's law. It's just a perfect, beautiful example of how a basic scientific idea can be engineered to multiply force and, well, move mountains. Or, at least you call.